Haruna, you can start.
Okay, ma'am. So now, as we approach the close of day three, we transition from quantum design to quantum detection, exploring how spins and diamonds enable some of the most sensitive and precise measurements in science today. With this exciting shift, it is my absolute honor to welcome back Professor Kasturi Saha, a pioneer in quantum sensing, nanophotonics, and experimental quantum technologies. In her previous lecture, Professor Saha gave us a comprehensive overview of quantum estimation theory, tracing the evolution from classical Fisher information to its quantum counterparts. She also discussed key concepts in quantum systems like two-body implementations, classical detection techniques, photo detection, and noise effects, setting a strong foundation for understanding precision measurement at the quantum scale. We look forward to her continuing continuing insights as she guides us deeper into the fascinating world of precision quantum sensing. Please join me to welcoming Professor Kasia to the stage. The platform is all yours, ma'am.
Hello, can you hear me now clearly?
Yes, ma'am.
Okay, okay, good. So I'll just do full screen. Is it in presentation? Can you also see the presentation?
Yes, ma'am.
Okay, okay, okay. Thank you so much. Thank you once again, and I'm very happy to be back again to discuss more about quantum sensing. And today I will be telling you about the landscape of quantum sensing. So Savna very nicely summarized what we discussed yesterday about going from classical detection to quantum detection and what are the key things that we have to keep in mind when we are talking about sensing and a parameter estimation. So with that, a starting point, here is, a set of things that, quantum sensing really covers. So in yesterday's lecture, I showed you some pictures of quantum sensors 1.0. And also some true quantum technologies that we are actually focusing on. I also mentioned about atomic clocks being one of the pioneering quantum sensing technologies that we have been seeing as being developed as one of the oldest techniques for being developed across the world, along with atomic clocks, which is definitely one of the most important areas of focus for timekeeping across the world. There are also many other quantum sensing and metrology domains. For instance, quantum magnetometers is what I'm going to really focus on today. It is my expertise, and I will be talking to you about one specific type of magnetometer today. As you will see today in the lecture, there are so many different types of magnetometers, and they all work very differently. But I will only talk about one thing. Uh, Yesterday, I also touched upon a few other things, for instance, photo detectors. And I described photo detectors in the classical sense in quite a bit of detail. But we did not really talk about the quantum photo detectors, which is essentially used for really noting single photons, meaning a single number photons. So you might be hearing in the quantum networks or communication lectures about single photons, which are actually Fock states or number states of light. Here, these photodetectors are actually number resolving detectors, which are superconducting nanowire detectors, and they work in the true quantum regime. There are also bolometers, which also work in the true quantum regime. Again, are number resolving detectors. So this is also, in a sense, this is also sensing because we are actually sensing photons, and therefore photodetectors are quantum photodetectors also fall in the domain of quantum sensing. Um, in terms of electrometers, or meaning if you want to measure, electric field, then there is, or very precise electric field, then there are ions or and ion traps, which are, or Rydberg atoms, which are one of the type of quantum sensors that are used for measuring electric fields very, very precisely, and go down all the way up to a few hundred nanovolts per square root hertz. So that's the typical kind of sensitivity of some of these very, very precise electric field sensors. Uh, the domain of quantum inertial sensors is very interesting. There are, as you know, the classical version of the sensors are usually are MEMS devices. So, as you may be aware, that your phone has, an accelerometer, which is essentially telling you what is the direction in which, when you change your, if you rotate your phone, you see your screen flip. The reason it can flip is because it can actually detect the MEMS gyroscope actually is able to detect, or accelerometer is actually able to detect the change in the rotation of the phone. And that is because it is able to detect, it's a rotation sensor. Now, rotation sensing is typically done with respect to some reference frame. But when you want to build a sensor or a rotation sensor that is independent of its inertia, independent of any kind of reference frame that you're measuring, or it is self-calibrated, then it's an inertial navigation sensor, or it's an inertial sensor. This is very important class of sensors because if you want to do GPS free navigation, then inertial rotation sensors or inertial sensors are one of the key type of sensors that one has to develop. So this is another very big area of sensing. Further moving on, there are gravimeters. So quantum gravimeters, like which sense very, very low changes in the gravity, the field of, and this is gravimeter. So again, these are also very useful devices, particularly for if you're going deep in for deep mining and oil finding in oil, etc. These are mineralogy. These are very extensively used, and also up in the hills, etc. So gravimeters are very useful, again as anomaly detectors as well. Uh, so another set is of course the magnetometers, which I will be describing quite a bit in detail. This is another sort of frame of the same thing that I just mentioned in the previous slide. Just to give you a little bit more detail into the type and the class of sensor we are discussing here. So I just described, development of quantum sensors here. Amongst the magnetometers, there are SQUIDs, atomic magnetometers, solid state based sensors. Then for inertial navigation and rotation, we have atomic gyroscopes as well as solid state based gyroscopes. We also have MEMS gyroscopes, which are the typical gyroscopes that are present in your cell phones. But they are not quantum, they are very classical, and the atomic gyroscopes are very quantum. Gravitational field detectors, so atom interferometers, especially like the version that is used for atomic clock, can also be used for doing gravitational field detection. These are atom interferometers. And then you have magnetic anomaly detectors. They all form under the gravitational field detection. In terms of electric field sensing, we have voltage sensors, resistance measurement sensors, and current sensors. We also have charge sensors, which is not mentioned here. These are all unique, different kinds of methods and techniques. And as you can see already, this is a very large class of measurement devices. Uh, in terms of sensing molecules, which is also another very important domain of sensing, which is for could be a fluorescence resonance based sensor or a solid state NMR based sensor. These are typically used for biology and chemistry for detecting different types of molecules for drug discovery, for healthcare, etc. And as you can see, this is a very large list, and also there are many more set of sensors. This is not a complete set of sensors here, uh, but this is a very diverse set of domain which falls in this category of quantum sensors. In terms of precision metrology, uh, we have the atomic clocks and we also have the optical clocks. These are two different techniques that are used for timekeeping and time standardization across the world. Various different groups of, this NPL is an example of a place where atomic clocks are developed. And similarly, there are several such national physical laboratories across the world, which are, which have been tasked with the mandate of keeping time. And NIST, for example, the picture that I showed you of this one is one of the foremost, atomic clocks that maintains time across the world. Similarly, we have two other domains, which is quantum enhanced imaging, and briefly mentioned it yesterday. For instance, if you really want to do imaging with very low photon number or through turbulent media, where you literally cannot see anything through, say, fog or a lot of clouds or cloudy media, then you would like to use these kind of quantum enhanced imaging techniques, and these are some of the things that are very novel, very new all across the world, and are being developed in a very nascent stage. And then there is quantum limited metrology, which is finally, if you reach the ultimate stage of metrology, what are the methods for reaching ultimate sensitivity or fundamentally limited sensitivity? Is something that many people are working on at a very fundamental level of understanding how to do metrology very precisely. So, setting this landscape, I want to now talk about something that, of course, is warfare is something that we want to always we are adversely affected by. But however, this is truly something that is that leads to the development of the highest grade of technology, and it has been there for quite some time. Across history, if you read history, you will find that technology development is very closely related to warfare. And so therefore, this is just a picture to show how different technologies ultimately link up with each other. For instance, if you have quantum sensors that can be placed in submarines, or it can be used for radars. Quantum radars are also detecting detectors or quantum sensors. Then you have quantum chemical detection. These are all different types of quantum sensors. Similarly, you have inertial navigation, which will allow your rockets to fly by itself. It will have its own navigation, GPS free navigation system. These are all sensors, and then linking these sensors are the communication channels that you have, that could be, essentially be part of the communication, the quantum communication protocols that people are developing for not only ground to ground, but ground to, out in space, and then, space to space kind of interaction with each other. And finally, when all of this have to be connected to a computing device, we need the quantum computers, and they all finally have to be linked with what is known as the quantum internet. And hopefully, as we see, these different domains are all currently coming up parallelly in this country through the National Quantum Mission. We are focusing on all the domains, whether it is quantum communication, or whether it is quantum sensing, or whether it is quantum computing, or even quantum materials, which is another, the fourth vertical essentially. uh, they all finally link up through the formation of interconnected quantum sensors, and finally interconnected through quantum internet, and hopefully will be used, and there'll be secure communication through the protocols that are being developed by the quantum communication experts. So, with this in mind, let me give you some more examples, because today we are really talking about the landscape of quantum sensing. Uh, Let me give you some examples more of healthcare. So, here you see is a picture. This I have actually taken from IOP reference. I forgot to put the reference here, but this is from a journal paper itself. You can see the kind of different applications of quantum sensors for healthcare. One application could be possibly through the detection, of inside the cellular environment. If you could do quantum sensing, so for instance, you could do temperature sensing, or you could do a local change in pH, or you could measure a local change in reactive oxygen species. These are all can be detected by quantum sensors. So, microscale structural determination to temperature probing in living cells. These are some of the technologies which are being developed across the world. On the other side, we can see that there could be a potential of developing, technologies that can enable us to image neuronal cells. At the same time, we should be able to understand how the neurons actually talk to each other. And this I also work on personally myself, and some of this in my group as well. Then there's another class of sensing, which is essentially looking at chemical sensing, or inside a battery if you want to sense, so for here as well, inside a battery if you want to sense the different kind of changes that are happening through magnetic field sensing. These are all applications that are possible with the new and upcoming quantum sensors. Moving on to another very big industry, which is the automotive industry. And automotive industry has many different applications, which are also very useful, and where we also need quantum sensors, the precision of quantum sensors, to really enable us to go to the next generation of automotive industry. So let's start from here. We have navigation and autonomous driving. I also already mentioned this yesterday in one of the images, that autonomous driving or self-driven cars, if you think about it, the way you can make very precise self-driven cars is by being able to locate its position with respect to its surrounding very, very precisely. You don't even want one sound small thing coming in front of the car to avoid kind of collisions. So collision avoidance, uh, improving fuel efficiency, tire pressure monitoring, or battery management. Again, battery management is a very important domain because ultimately the health of a battery really determines how fuel efficient and how productive or how good your car is going to perform. Similarly, there are other aspects to automotive industry. For instance, you don't want your car to vibrate and have a lot of noise, etc. So vibration and noise reduction, emission monitoring. Again, this is gas sensing, literally. And driver so lots of different kind of things that come under the domain of quantum sensing, and you'll be surprised in fact, as I am interacting more with these different types of industries, I realize that there are so many different aspects to quantum sensing that even I am learning on the go. So now I will really jump into magnetic field sensing, which is essentially my core expertise domain. And here we are really looking into sensing extremely small magnetic fields. You are quite aware of, bar magnets or horseshoe magnets, and you have seen pictures of this from very, I don't know, from school days, etc. We use magnets in very typical routinely in fridges. Fridge magnets are very commonly found. Those are typically of the order of a few microteslas or a few hundreds of microteslas of field. But we are talking about much smaller fields here of measurement that we. So just to give you an idea of the kind of kind of scales that we are talking about of magnetic field. So a reference number is the Earth's magnetic field. So Earth's magnetic field is somewhere in the microtesla region, so it's zero point 0.5 Gauss. That's the average Earth's magnetic field. Now, it varies from places to places. For instance, if there is minerals, it may be quite starkly different from zero point 0.5 cows. And for instance, up in in the earth or deep in the ocean, also there are various different sort of topology which leads to different kind of Earth's magnetic field. Now, similarly, in there are other kinds of human structures that we have built across the world, like power lines, automobiles, screwdrivers. All these things all have different kinds of scales, as you can see, and they keep reducing. And cars typically are in the picotesla to femtotesla region. Okay. Now, in the biological scales, if I look at, the human brain, actually the neurons interact with little electrical pulses, and these are mostly of the order of picotesla to femtotesla, meaning 10 to the power minus 12 to 10 to the power minus 15 on time Tesla. And that is several orders lower than the Earth's magnetic field. As you can see, it's here, and this is the neuronal signatures are almost here. And then you also have these kind of um, our heart, actually, when it's beating, also has hundreds of picotesla, meaning somewhere in the microtesla region. You have the heart muscles also have a signature, magnetic signature, and you might be aware of ECG. There is also a magnetic counterpart of that, so it's called magnetic encephalography, and that is also a very well-known technique for monitoring the heart's performance. So, in nature, of course, magnetic field, because there is an Earth's magnetic field is very nicely sensed by hummingbirds, and hummingbirds or even turtles or any kind of migratory birds. They basically go from one place to the other very well, being able to sense the magnetic field of the earth, very precisely sense the magnetic field. And there is actually an ongoing debate on whether the sensing that these birds actually do is cross classical or quantum. And with recent publications, it seems that it is actually indeed a quantum sensing feature that is present in the bird's nose and eyes, and they have very very precise detectors which can sense very small tiny field changes, and hence they are able to keep maintaining their path and are able to reach very large distances almost across the world, and they can go for exactly from one place to the other remembering the location, which is another very remarkable thing about nature. So, like olive ridley turtles, I don't know. Recently, this is the season. Basically, they move from almost the east coast of uh, you know, um, subcontinent to west coast here. So we recently went to a coastline of Maharashtra where they have these olive ridley turtles that come back every year to hatch in the same place. And they are able to do this because they can actually sense the Earth's magnetic field and move and come from one place to the other, and go back exactly to the same beach that they were born. So this is very remarkable, something that we note of from the and what we can also capture from natural environments. If we could understand the processes, we could perhaps mimic these kind of sensors as well. Then there are other different types of sensors like receptive bacteria, and other types of different kinds of bacteria also exist, which are very receptive to magnetic fields. Moving on into magnetic field sensing, as you are aware, magnetic field can be from a very big range. So you have Teslas of magnetic field, which are used in MRI machines. So several Teslas, in fact, are used in MRI machines or NMR machines. If you would have seen one of them, there are like 7 Tesla machines, 11 Tesla, 9 Tesla machines. Etc. But then we just saw a length or a scale, physical scale, where the magnetic field is actually as low as picotesla or femtotesla. So we need a very large range of sensors which can cover that entire dynamic range. And obviously, one sensor is not going to be able to do that entire span. The other, if you see this axis, is actually resolution or the physical, the spatial resolution that the sensor can actually provide. So there are sensors that can sense the bulk amplitude of the magnetic field. There are sensors that can sense both amplitude and the direction of the magnetic field. Magnetic field, remember, is a vector quantity, so it has both amplitude and as well as directionality. And but there are sensors which don't have both of them, so you can see a gap here, that you don't have sensors that can have very good spatial resolution but at the same time also have very good sensitivity. So there's a huge number of sensors which are like Hall probes, etc., which are in the high or low sensitive region. So sensitivity actually is better if it is high sensitivity means small number, and so here you can see that in the micro Tesla region you have the Hall probes, etc. Then you have squids and vapor cell based or atomic sensors, which are some of the better sensors which go in the picotesla to femtotesla region. These are some of the best sensors that are possible for magnetic field sensing. Vapor cells are atomic vapor cells, and then you have squids, which are essentially superconducting uh, Josephson junction based devices. These are, however, cryogenic. Vapor cells can be room temperature. NV centers actually fall in a very niche regime where It is not one of the best sensors, but it at the same time it can also do very good spatial resolution. So in fact, this is a very old plot. I have to move this out here. So now NV sensors are somewhere here. Where you can actually get better sensitivity as well as better resolution in terms of spatial resolution. So if you really want to do some image, then this is the type of sensors that are to be used. Now, moving on, for the rest of this lecture, I'm going to talk to you about NV center based sensors and then some of the quantum sensing protocols. Now, these sensing protocols are not very unique to NV centers. It is pretty much uniformly used in all across all types of sensors. There are various different variations of it, but at the end of the day, you are essentially using a two-level system and using pulse protocols to control those two-level systems for performing sensing applications. So it's sort of general in that way, but what I'm going to tell you today are more specific to NP sensors. So now I start with what these NB sensors are. All of you have seen diamond. These are, very bright, crystalline, very highly crystalline crystals, and they are very shiny, very well known in the gemstone community. You have different types of colored diamonds as well. You have yellow diamonds, orange diamonds, blue diamonds, etc. And if you don't cut them or polish them, they actually look like this. And this diamond actually has a lot of nitrogen concentration. So when diamond is growing in the Earth's crust, a lot of nitrogen can replace the carbon atoms. So diamond ultimately is carbon atoms and is set in a lattice of FCCs interlinked with each other. So it's a diamond lattice and specifically. And so when you have a lot of nitrogen replacing the diamond, it gives it this very nice yellow color. If you have boron inside the diamond, then it gets it this blue color diamond. And if you have concentration, which is not, so you can't really make out whether it has any defect in it or not, depending on the concentration, it could be something like this. Now, uh, when diamonds are grown, diamonds can be grown in two methods, either CVD or HPHT. CVD is nothing but chemical vapor deposition, and HPHT is the high pressure, high temperature method. High pressure, high temperature method tries to mimic what happens in the Earth's crust, and CVD is a chemical way of getting carbon, pure carbon out. And this is what it looks like when it comes out of a CVD process where you have after polishing. So if you polish the surfaces, then you can get this kind of plates of diamond. And nowadays, these plates can go all the way up to wafer size. So standard, almost 1 inch, 2 inch wafer size, people can make these kind of diamonds. Uh, the nice part about making with the advent of these kind of diamonds, what you can get is you can use to fabricate now, do nano fabrication on these type of diamonds, and what you can do is make pillars, make structures, make nanophotonic structures, or you can go to the other extreme and crush them down and make nano diamonds. And nano diamonds are also very tiny particles of diamonds, which could be anywhere between 30 nanometer to 120 nanometer, or it could be even larger microcrystals of diamonds as well, which could have different kinds of impurities in them. The ones that we are interested in are actually pink diamonds. Pink diamonds are the ones that have the nitrogen along with the vacancy in it. So what we are talking about here is this is the lattice structure of diamond along with after you replace one carbon atom, you get what is known as the nitrogen, which is substitutional. And if you have a vacancy next to it with an additional electron, this forms what is known as a nitrogen vacancy complex. This nitrogen vacancy complex is very interesting because it has a fluorescence which is in the pink regime or in the red regime, and that is what gives it this diamond the very nice pink color. And this is the one that is used as the sensor. So, what is really this nitrogen vacancy center, and how do you really probe them? So, as you can see, this is again the crystal structure of diamond, and with the nitrogen vacancy center in here. Uh, in what we do is really shine some green light. It could be a green laser pointer, it could be a green laser, it could be a green LED, anything. The coherence of the light doesn't matter so much. It's a broadband beam. And then what we collect is the red fluorescence, which is a fairly broad band again, from all the way ranging from 630 nanometer to almost 800 nanometer. So it's almost in the red region, covers the red region. So this is the artificial defect. So this is actually an artificial defect. It's almost like an atom. It sits inside the diamond lattice, and it's almost like an atom, like a two-level system that is sitting inside the diamond, band gap. So diamond has a very wide band gap, so 5.5 eV in comparison to silicon, which is only 1.1 eV. So in that band gap, it almost seems like this is like a point defect which is sitting in the band gap and does not interfere at all with the rest of the diamond's, band gap, dynamics itself, except that it sort of steals one of its electrons from the lattice and kind of forms together what is known as NV minus state. And so there's an extra electron here which forms the NV minus. So the ground state of this NV is actually a triplet. You have the 0 and the plus minus 1, which is degenerate, with a 2.87 gigahertz as the zero field line. When we shine the green light, it emits red fluorescence, and that is how we can measure this. And so, what you see here is actually a confocal image of this crystal. So, if we have a crystal with very tiny, tiny point defects in them, so these are tiny point defects, could be single emitters, could be single NV centers, or could be maybe one, two NV centers in them. And once we focus here, you can see the bright emission that is collected from these point defects. Ultimately, the NV center is actually just a two-level system if we use one of these two levels here. And that can be represented on the Bloch's flow. So let's see how this NV center actually operates. So what we do is assume that all the NV centers that we have are in different population or occupying different states of the ground state. As we shine green light, we can see that it gets excited and it will then get de-excited. Sometimes it will remain in the states that it will be. But as you keep shining the green light, what can happen is that every time there is one metastable state here, which it can traverse to, and then it can come down only to this ground state because of the allowed transitions. So once it goes to this metastable state, it cannot anymore go to these states. It can only go to this state. And so if you keep shining the green light, what happens is that you come down to the pure ground state. Now remember, in yesterday's lecture, I actually mentioned that as a counterpart to the De Vincenzo's criteria, which is for quantum computing, we also have criteria for quantum sensing. And for any quantum system, one of the most important things is to be able to create a state or initialize the state. And here you can see that we could very nicely initialize this state of the in the center just by shining the green laser. And if you keep doing that, you can create a very nice pure ground state. But what about readout? We also need to read out the state. So for any quantum sensing protocol, after any protocol, we have to be able to read out the state. So how do we read out the state? So the process is very similar. We keep shining green light and we keep collecting the green light. And what we observe is that the unique property of any center is that there is a difference in the fluorescence when it starts from 0 versus when it starts from plus minus 1. So it is actually fluoresces lesser if you start from plus minus 1. So you can see that there is a contrast difference between the population if it starts from spin plus minus 1 or 0. So what we have observed is now we can do an optically detected magnetic resonance, or meaning I can detect a spin resonance by or spin state by doing just fluorescence intensity collection. So this is the way I can read out whether it is 0 state or plus minus 1 state. So our operation of NV centers is therefore we apply a bias field which will enable us to split the plus and minus 1 levels by just doing a Zeeman split. So this is the standard way in which you split any kind of electronic spin state lines, which is by using Zeeman splitting. And in this Zeeman splitting, the B field actually separation of energy which is equal to gamma b between the two lines here. And by probing this resonance, now we should be able to see what is happening to the magnetic field. So let's start with our process. What we do is we measure, and we initialize the state, and that could correspond to somewhere here in this fluorescence chart here. And then as we sweep this frequency, so we apply a microwave field and try to control the spin. And what we see is that as we change the microwave frequency, we can trace out something like this, which is essentially my optically detected magnetic resonance. Now, if obviously if these two lines actually change with respect to each other, or if this line changes, then this resonance frequency will change, and that is what you see in this dot dashed curve here. So if the resonance changes, you get a dashed curve which looks like this. So any shift in the magnetic field, it corresponds to gamma, which is gamma equals to 2.8 megahertz per Gauss. Because this is an electronic spin, it's got given in terms of how much movement it will see because of the magnetic field. Uh, so we can then map out the entire shift in such kind of a magnetic field for NV centers, and you can see a very nice Zeeman splitting of the two 0 plus transition, plus one transition, and 0 minus one transition. And if you see, the fluorescence is also very nicely closely linked to those transitions, and near somewhere around the 500 Gauss line, it actually, there are more complicated things that happen. And so today we are not going to talk about that, but there is more interesting physics that goes on in these kind of systems. Okay, so just to go back to our very simplistic picture of a two-level system, we now have a 0 plus 1 or a 0 minus 1 as the two-level system. So we start with here. What we can do is we can initialize, and now if you remember yesterday, I said we can give a pi pulse. So we start giving a microwave pi pulse, and you can see that it can transition from 0 to pi, and then as you keep changing the microwave driving, you can control the spin way as however you wish. So basically anywhere on the equator or anywhere on the surface of this sphere, you can by applying the right kind of microwave driving. So this is essentially called Rabi oscillations, and so what you're seeing here is basically a plot of the Rabi oscillations. Now, interesting thing about NV centers is that it's a fairly complicated Hamiltonian, and that is what makes it a very complicated sensor as well. It can sense not only magnetic field, it can sense electric field, strain, and temperature. So what temperature does, it actually changes the zero field splitting, which is this 2.87 megahertz, gigahertz. And then if you apply the B field, which is your first, so Zeeman split, so you can see that this is changed, and so you can then get two additional lines, which is what you see as the two gamma B in a parallel. Now, if you keep applying more, interesting things will happen is that you see not only two peaks, but you also see three peaks here, which essentially corresponds to the hyperfine split because of the nuclear spin of the nitrogen that is interacting with the electronic spin of the NV. So you have an N14, or if you have an N15, you get two of them each. And all of these are all now, this is just the electronic Hamiltonian. This is not the nuclear spin Hamiltonian. You have the nuclear spins along with this. So electric field actually couples as D dot E, strain is M dot Z, M dot S, and D is essentially because of this. The zero field splitting changes because of temperature, and this is also a way to monitor temperature. Another property of the NV center is that it is a vector magnetic field sensor. And the reason it is a vector magnetic field sensor is because in an NV, in a diamond lattice, there are four possible orientations of NV centers, or NVs that are along each of these bond lengths of the 111 lattice. So you can have four possible. So if you have a B field which is in arbitrary direction, you can then have 4 on one side and 4 on the other side, which is about the 2.87 gigahertz. And you can also align the fields correctly, and that will give you four equal axis, or you can have zero field or single axis alignment as well. So there are different things that you can do depending on the kind of magnetic field that you apply and how you really control the system. So moving on, in a very small kind of a nutshell, NV centers can be used as magnetic field sensors, temperature sensors, and as well as strain and electric field sensor. It is interesting to note that each of these lines actually move in very different way. So the coupling to the Hamiltonian is such that you can actually distinguish between the magnetic field and temperature and strain, etc, and two of them at least you can do simultaneously. So by just looking at the frequency changes with respect to the applied field or strain or temperature, etc., one can actually recalculate back the vector magnetic field as well as the temperature changes, etc. So this is very important and very unique kind of a sensor which can do dual sensing as well. Now I'll go back to the things that we discussed yesterday. Let's go back and try and see how magnetic field is really, so what are we really doing? Remember yesterday when we discussed parameter estimation, I said that most of the time what you want to sense is not what you can directly sense, right? So if you want to estimate an parameter, for instance, here we want to estimate B, but we are not really sensing B directly. We are sensing B through through the fluorescence, right? So what we are actually capturing is the intensity of light, but what we are sensing finally is B. So what is the sensitivity of B then? In this case, our signal that we mentioned, the variance in the signal by the slope. So let me just go back again here to my very nice picture here. So if you remember from the exercise that we did in yesterday's lecture, I mentioned here that if you what we want to see is the change of the B field because of the thing that you are trying to measure, right? So, or change of the fluorescence because of the B field. And where does the fluorescence change the most in this? It is actually in the slope and not in the maxima, right? So if you just measure the intensity, that is not the best point for measuring the B field. What you want to do is actually sit here, and that is where your intensity changes the most. So your B field changes the most because, or y-axis, if you take a derivative, you will immediately see that this is the point of maximum change, and that is what we even see here when we are defining the sensitivity. It is the variance or the noise in your data or the intensity data divided by the slope, which is essentially your signal by the B field. So this is which is the Kramer-Rao bound, and this is the short noise limited sensitivity that we can measure. Now, just to summarize again, if you have n such qubits, meaning you don't have just one sensor, but you have many such sensors, then your sensitivity will improve and you get a square root of n advantage of measuring the B field. Now, if you measure more number of times, of course, you have the number of sensors plus you have this advantage here. Now, ultimately, what you would like to do is really go to the entangled state, and that is where you get the 1 over n advantage. And this is the interesting point at which different NV sensors may try to interact with each other and form these very pure entangled states, which can lead to better B field sensitivity. Or so finally, the fundamental limit of our sensitivity is going to be the standard quantum. Beyond the standard quantum limit is 1 over n, by creating entangled states between different of these single NV centers itself. So from this, you can already see, even if you don't go to the entangled state, you can see that an ensemble NV center is much better than a single NV center when it comes to magnetic field sensing. So if I want to get a better sensitivity, then I want to use a very large number of sensors, or square root of n advantage, to be able to get the best sensitivity. So the more the number of sensors I have, the better my sensitivity, or the smaller my B field resolution will be. Okay, so going back again, it is definitely true that we cannot, these are not very easy things. You can't just get it out of the, if you just go to the market, you can't buy these sensors. You have to prepare, you have to know how to prepare them, measure them. These are fragile and quite, they also decohere. Uh, they also have parameter spatial inhomogeneity. As you can see, if you have a distribution of NV centers, you need very high density of NV centers. Creating such kind of samples is not very easy. And how to create these samples is one of the very key difficulties in this field itself. Of course, then there are many limitations like the coherence time and the parameter variations, etc. So it is challenging, but it is developing, and there are many things that are going on, which I will discuss. So let's try to now start doing some sensing, which is going back to our protocol here. So far, we have seen in the NV Center system itself, a real true quantum system, how to create and initialize this state. Then how do you transform the state by applying some pi pulse or pi over 2 pulse, etc. And then you let it evolve. So if you just let the system sit in its own environment, it will evolve, which is it will change with time. It will feel the environment. If it couples with the environment, it will feel the environment, and then it will come to a new state, which is psi of t. And what we now have to do is project and read out the state using the optics that I just discussed. You can project and then you can read out the state of the system. And of course, because we have seen that we are limited by the noise in our system here. There can be optics noise, there can be laser noise fluctuations, there can be microwave fluctuations, there can be heat changing in the system. For instance, the sometimes it happens in our lab itself that if your AC is fluctuating, we immediately see that in our data because our sensor is actually very good, and it senses its environment very easily, and what you see is fluctuations in our data. And for this, we have to actually average and keep track of many different parameters within a very controlled environment we have to do. And however, it's a two-way thing. So it is performing like the better sensor that you want it to be. Of course, it is sensitive to its environment, and so you have to make note of that and repeat multiple times and then estimate the signal finally that we want to sense. Okay, so now I want to really discuss a few things about magnetometry and the kinds of magnetic field sensing that one can do. When I showed in the first slide, what you have seen here is what is plotted is if you have different magnetic fields, your lines will shift with respect to each other. And when you have your field shift, you can easily sense through the frequency shift, right? So it's gamma is given by 2.8 megahertz per Gauss. So for every 2.8 megahertz, you have a Gauss change in the field. So correspondingly, you can just scale it accordingly. Now, as you can see here, this is DC magnetometry. Basically, just by doing a simple ODMR, you can find out what the magnetic field is. It's very simple. You can measure the frequency here, and then you can measure the change in the frequency correspondingly. Now, if you want to do one step further, then what is known as Ramsey type magnetometry, or analogous to an atomic clock. Actually, this is what atomic clocks also do. They do a Ramsey type experiment where you essentially initialize the spins along one of the directions, and then you apply a pi over 2 pulse. So you flip it. So this is the x pi over 2 pulse. You flip it, and then it comes to the equator. And then, if you remember, we discussed about the phase yesterday. So that phase is given by gamma b sigma z. Sigma z is nothing but the spin, and then the gamma b is essentially the b that it feels. The phase, the delta phi, will change with respect to that field. And when it changes with respect to that field, you can see that it will acquire a phase. And what it will do is it will change this spin's location on the equator. So once it changes the spins on the equator, its phase on the equator, what you see is it's gone from the plus to the minus here. Now what you want to do is apply one more pi over 2 pulse, and then actually read out the spin state. Okay, so this is something that we can easily do, and this is what gives us what is known as what is extremely well known in literature as Ramsey experiment, where this is the most sensitive kind of DC magnetometry experiment that one can do. And we can actually get the B field out of this by just doing a simple Ramsey, which is by applying two pi over 2 pulses. And what you see is essentially the fluorescent signal kind of oscillates back and forth. And if you just fix a time, and then you can sense this field. Now, the next thing to do is essentially go to the next type of sensing. So here we can only sense DC fields, but what about AC fields? So we'll go to that. But then there are different types of other kind of ODMRs are also possible. So we have CW ODMR. We have pulsed ODMR. So what we can do is, apply a CW pulse and CW microwave, and then we can just read out. Or we, to avoid the noise because of the laser here, one can also apply pulsed lasers and then only do a pulsed pi experiment. And this is a kind of a pulsed experiment. And these are different types of sensing regimes. And this is the net sensitivity experiment. What is the net sensitivity that you will get because of a Ramsey experiment? You can see that the spin projection limit is finally given. Ultimately, this is the true, limitation of our system, where we have it is limited by the spin projection noise. Uh, and that is the number of sensors here. Then you have the spin dephasing, which is essentially that you cannot have these fluctuation remain there for forever. If it were a non-decohering system, then you would have the Ramsey, or meaning the oscillations over in the across the equator forever and forever, and it will not decohere in its actual length. But what happens is that this signal actually dies down, and this is the decoherence that we're talking about here, which is limited by T2 star, or spin dephasing here, which is given here. And then finally, because we are reading out with optics, what you have is actually dependence on the collection efficiency itself, or the light collection efficiency itself. And because diamond is a very high refractive index material, so what happens is it actually traps the light quite a bit, and so you don't really read out the optical or the spin state, because most of the light is actually trapped inside diamond. And so this readout is also another very important parameter. And then finally, whatever is the readout overhead time that you have. There are other different types. You can read this reference here, how to calculate these different kinds of sensitivities. Uh, you can also have, finally, what happens is that the sensitivity is actually limited by the readout fidelity, the number of spins, the dephasing time, and the overhead time. So if you have a many spin magnetometer, what people have seen is that uh, it's true that the sensitivity will improve up to a point where you increase the number of spins, but ultimately it will come down, because the spins start highly correlated and become highly correlated, and it can actually interfere with the sensitivity itself. And so you really cannot use this just too many spins, but you have to have a right number of spins to make the magnetometer. Uh, so there are many different other techniques for measuring the magnetic field. For instance, AC sensing is one of the ways in which, where instead of DC magnetic field sensing, suppose if you wanted to sense an alternating field, then how would you sense that? So there is a technique called Hahn echo, which is nothing but applying another pi pulse in between to sense this alternating magnetic field. And there are many different types of such kind of pulse sequences, which it's very well known in the NMR literature, where Han, CPMG, N types of CPMG. There are many different types of experiments, and based on this, you can have different regimes of sensing, whether it is DC or whether it is somewhere in the megahertz or gigahertz regime, etc. Now, I just want to quickly show some of the experiments, how they are really done. And you can see that what we finally apply is a polarized light, and then we have a microwave of readout light, and you have a microwave on, and then finally another readout, and what you get is something like this. If you now zoom in, we get very nice hyperfine levels as shown here. You can drive them. This is the Rabi that we were discussing. And then in my lab, we have observed that we can get almost about 1 microsecond of coherence time. You can do echoes. These look beautiful echoes here. The modulations that we see are because of the nucleus pin interactions that are going on inside the system. Uh, so I want to now talk about the applications of these kind of sensors and where the NV centers can become very prominent and useful. So what you have is, of course, magnetic field sensing is one of them, and it can be maybe attached to a drone for doing mining research. You can do anomaly detection. Another recent paper that had come up during COVID times was if you have these nanoparticles of NV centers or nano diamonds in them, and you have NV centers in them, you can do virus detection through this SARS-CoV virus. There's a paper that demonstrated this SARS-CoV virus detection, even in a microfluidic chamber environment. So one can do microfluidic NV center kind of experiments using this type of geometry. The way forward would be really to push it to this regime where you have the NV centers can be attached to, like an MRI machine, can be attached through probes here for doing functional MRI kind of experiments. Uh, Another application is essentially to have nanodiamonds inside cells and do local temperature measurements. And local temperature variation, as we understand, is one of the key parameters of cell health detection as well. Um, to show you that there is a very large range of applications of these kind of sensors, here are two other examples where we have a single NV center interacting with proteins that are not crystallizable. So what you can do is broadcast proteins that are not crystallizable, and then finally you do an interaction test, meaning you measure the interaction between this NV center spin with all the nucleus spins that are sitting in this protein, and you can measure the dipolar coupling and nucleus spin uh, through various different pulse protocols. And what we can find out are what are the different frequencies in which they interact, and from there we can actually estimate what this structure is really. On the other side, using a single NV center, you can also attach it to an AFM tip. This is a very well-known technique now. You can attach it to an AFM tip and scan it with over a flake or something like this, and be able to study its local magnetic field properties of, say, 2D materials or 2D flakes, or magnetic flakes which can have distributed magnetic fields across the flake. Now, I want to talk about a class of magnetic field sensing, which is not just sensing but also imaging. And this we do routinely in our lab now, which is the method of quantum diamond microscope. So instead of using a single NV center here, what we have is a layer of NV center, say a 1 micron NV center layer. And the reason we have to use a layer of NV center and not really the full bulk of the NV center is because if you use a layer, only then we can get the spatial resolution that we are looking at. If you have the full NV center, then because magnetic field is a vector quantity, you essentially sense and average out throughout throughout the sample. So what we do is shine the green light, and instead of putting it on a photodetector or an LPD, we use a CCD camera here, and then that CCD camera actually maps out the per pixel distribution of the fluorescence over a large area that which we shine the green light here. And this allows us to image the full area which has a distribution of the optical light, and this will also then enable us to find out the changes in the magnetic field in the spatially resolved way. So this is a way in which we can do just like light microscopy, where you can do zoom into different optical features. Here we are looking into different magnetic features in wide field, and wide field means here you're looking at almost 200 micron plus 200 micron area uh, of the field. Of course, you can also go much larger area, almost millimeter size, but then it is a catch 22, because you have to balance it with the kind of per pixel sensitivity you have with the field of view that one can actually achieve. So the applications of such kind of quantum diamond microscopy is very wide scale. One of the things that I want to start with is fundamental physics here. So you can look into samples like superconductors, see vortex dynamics, or even study like current J reconstruction. So one can also do J reconstruction or current density reconstruction using the magnetic field features themselves. And these are some of the things that have been done in the recent past. However, there are biological applications as well. So, for instance, you can look into like one of the things to study is this, hummingbirds, and we want to understand whether it's truly quantum or not. Then one can actually have these slices of these cochlear cells on the diamond itself and be able to image. Similarly, an interesting example that I am very much focusing on is essentially neuronal imaging, where you can actually image. This is a C. elegans worm. It's a worm that actually has one neuron only, so it's not a cluster of neurons. So you can see here that this is the signal that one can actually measure using these MB centers. So in the next few minutes or so, I will just give you a quick overview of what we are doing in my lab. Where we are actually trying to see if we can image these neurons. We are essentially using the magnetic field microscope to mimic and image these neurons themselves. And what we are doing here are making circuits that actually mimic the neurons and measuring and flowing currents through them and then measuring these currents. So we use a technique which is not the simple ODMR that I have been discussing and describing so far, but what we do is actually a frequency modulated version of the ODMR. So instead of just applying a continuous wave frequency, we actually pulse the frequency, and what you get are derivatives. And this gives us even more sharper slopes to work with. And this gives us better sensitivity, of course. So I won't go into the full detection and lock-in detection method, but what you essentially will see is nothing but the same thing where you have with the field on versus field off, you have a change in the slope here. So you can see that there's a very distinct movement because of the field off versus field on. And this is what gives rise to what you can see here. I'll show you a video. And this is where we have made these microstructures and microcoils. And what you see are real-time images being captured of the microstructures and microcoils, which are being imaged by this microscope itself. We have patents for this, and this is now what we are going to do to extend it into 3D imaging, etc. So, with that, I will thank you very much for your attention, and I can take some questions now. I'll stop sharing.
Thank you. Thank you, Professor Saha, for that insightful and engaging presentation. Although we began a bit behind schedule, we
Mhm.
sincerely appreciate how smoothly and clearly you delivered your talk, keeping perfectly within the allotted time. Your talk provided a comprehensive and insightful overview of the evolving quantum sensing landscape, especially its emerging role in fields such as biomedical diagnosis, automotive applications, and magnetic field sensing. The segment on magnetometer application areas and also the DC magnetometry was particularly fascinating. What stood out most was your clear and captivating explanation of diamond based quantum sensors, especially how color defects in diamonds can be harnessed for precision measurement at the quantum level. Thank you so much once again. Now we will open